Hello, everyone, and thank you for joining us today for part 2 of our high-flow bioretention series, The Current State of Bioretention Research. Before we start today's presentation, we would like to cover a few housekeeping matters that will ensure you have a good experience. We have placed all phones on mute to cut down on background noise and to ensure everyone can hear the presentation. At the conclusion of today's webinar, we will provide information on how to obtain PDH credit for today's presentation. Our webinar today is scheduled to last for 1 hour and will include a question and answer period. If you have a question, please type it in the question box at any time. Today's webinar will be presented by Tamara Mammon and Vaco Allen with our special guest, Dr. Bill Hunt. If you attended part 1 of our series, The Advancement of Bioretention and Stormwater Treatment, you may remember Tamara and Vaco as the presenters. And if you missed part 1, don't worry, a link to the recording will be sent out in the email following the webinar. Now I'll turn the presentation over to Vaco Allen to introduce our special guest speaker, Dr. Bill Hunt.
Hi, everybody. Thanks for joining us again. Yeah, it's my pleasure to introduce Dr. Bill Hunt. You can read his bio there, but I'll just pluck a few things out. It's been about 20 years or so that I've appreciated his research, and I know that he and the team of grad students that he seems to always have employed there are really answering and asking the most relevant and right questions, especially when it comes to bioretention research. So when we thought about who we'd like to have join us here, it was really kind of an obvious choice, and glad that he accepted. So, there's been a long, rich history there. I think 250 or so BMPs that he's been involved with, either designing, testing, or otherwise keeping an eye on. Also 130 papers over the years. So a deep well of information there, and we're glad that he's here to share it with us. So here we go. Thank you.
Thank you. Well, it is a pleasure to be here, and I really appreciate Contact Engineering Systems for the invitation. It means a lot to me that you want to be a part of it, and I welcome however many hundreds of you that are on this, and hopefully you can enjoy your next hour and maybe even laugh once or twice as we go through bio. It's not like a super funny subject, but we'll see if I can get you to laugh. And there's a couple of times where I do show some work by Dr. Alan Davis, a good colleague, good buddy of mine at the University of Maryland. And you'll note that because usually it's like a turtle in the upper right-hand corner of the slide. Okay, so what is bioretention? Well, it is a media that is vegetated, that stormwater drains through, and it's incorporated as part of green infrastructure. And it is, in many places, such as North Carolina, risen to be more or less the second most popular practice used in our state, as long as you don't include swales and conveyances, but second most popular practice now after ponds. So it's a very popular practice that gets used across not just North Carolina, but lots and lots of other states, which is, I think, part of the reason why y'all are here. So I get 30 minutes. And in my 30 minutes, I want to answer 3 questions. One, how deep does your media need to be? And that has been, it's not necessarily recent research, but it is evolved research. We'll talk about how deep that media needs to be. Another thing, now that practices have been in the ground for a while, we can much better assess how long the bioretention cells are going to work. So we'll look into that for a little bit, and then I'm going to close with multiple ways that you can take a practice that works well and actually make it work even better. So how can you retrofit a bioretention cell, and what type of benefits do you get out of that retrofit? So in North Carolina, like much of the Chesapeake Bay to our north, we really worry about nitrogen and phosphorus. It has led to major lake closures. It has excess nitrogen and phosphorus, leads to hypoxic zones, fish kills, and the like. And as a result, a lot of what we have done in North Carolina has focused on how to better manage nutrients coming off stormwater. So I want to ask y'all to get some sense of where we're coming from, is what pollutants, if you could pick one, like what one pollutant do you think sort of motivates the design work or the need to stormwater in your jurisdiction? So Jill, I'm gonna hand over to you. We're gonna find out what the audience says.
Thank you, Bill. Here's our question. In your jurisdiction, what one pollutant's removal concerns you the most? Nutrients, temperature, pathogens, metal, TSS, or other? We'll give you some time now to mark your selections. And just a reminder, if you have a question, please type it in the box and I will ask it at the end of the presentation. And also we have included 3 handouts that are in one of the drop downs in the GoToWebinar toolbar. You can find our Filterra Solutions brochure, our Stormwater brochure, and our Site Solutions brochure. So when you have a moment, please check those out. I'm just letting it tally. I'll give you guys a couple more moments to mark your selections.
I'm excited to hear what people care about, Jill.
I know, a couple more seconds and I'll show you.
I will wait with bated. I actually can't wait with bated breath because I know you're not going to make me wait that long.
And that's right, I'll show the results right now. 37% say nutrients, 1% say temperature, 6% say pathogens, 11% say metals, and 45% say TSS or other.
All right. So much like our first go through 3 hours ago, this audience really seems to care about nutrients and then TSS. Maybe not in that order either, TSS and the nutrients. That's good because I will definitely talk about nutrients, but I will hit on a bit of metals, a little bit of sediment, a little bit on pathogens too. For the 3% of you that cared about pathogen, it was a 3%, Jill, that cared about pathogen, or 6?
It was 6%.
6. All right, good. 6. That's great. We'll get to that in a little bit. So let's first answer this question: how much fill media do I need? And I know why people ask it, because it is the most important question to determine how expensive that bioretention cell is. Obviously, the more media you need, the more you have to dig. All right. The more media you need, the more you have to buy. The more media you need, the more you have to ship, and the more media you need, the more you have to place. When you add all those things up, that has a pretty big price tag associated with it. And if you were at all involved in bioretention years ago, you knew the answer was 4 feet. That was the default. Okay, 4 feet. You got to use 4 feet. Well, first of all, it doesn't really need to be 4 feet much of the time at all. And we'll get into the rationale behind that in a little bit. But when we do decide how deep the media needs to be, it's really predicated upon 3 big factors. 1, can your vegetation survive? In fact, not only survive, but in many cases thrive with the amount of media that you're providing. 2, are you able to meet hydrologic goals? Obviously, well, maybe it's not obvious, but I'll tell you, for you, the more media you have, the better you are able to transition runoff or translate runoff to infiltration or evapotranspiration alike. Or do you have, what type of water quality needs do you have? What pollutants are you worried about? You're worried about sediment? You guys are worried about sediment. But a lot of you also worried about nitrogen and phosphorus. A few of you are worried about temperature. Well, based upon that one pollutant you're worried about, what's your best bet? And what we would suggest is whichever answer to those 3 questions, those 3 bullets, the black ones in black, well, whatever's the most restrictive one, well, that's the one you're probably going to want to choose. So let's start off with vegetation depth. Now, bioretention vegetation actually does not need a ton of media. Grass, which is successfully employed a lot, actually can handle 1 foot. You know, you can do all right with 1 foot. Shrubs, you add a foot on, 1.5 foot onto that, and then trees and shrubs, a tree shrub mix, you might add, the media might be a little bit deeper. All right. Having said that, the deeper you make your media, the more resistant that vegetation is going to be, because there's more moisture available to it during dry periods. But for the most part, we're not observing the vegetation requirement being what dictates that minimum soil depth, which gets us now to the potential for hydrology. I'm not going to name the big box store that allowed us to study here, but just know there was a big box store that agreed to allow us to do some study at their site. And the purpose of the study initially was to take a look at the benefit of having 2 foot of media versus 3 foot of media as your depth. We also made what doesn't really show up here, but we also made a retrofit about a year in. And so we actually had 2 sets of monitoring periods. I'm going to talk about data very quickly from both. What I want you guys to focus on are the 2 depths, the 2 and 3 media depth before. And essentially, before we made this retrofit, we added when you had a foot of extra media, you put roughly 10% more water into the ground. All right, that when you bought that extra foot of media, you got 10% more water going to the ground. After we made our retrofit, we studied it for another year, and again, the numbers were different, but we put 10% more water essentially into the ground. So you get some sense that, I mean, was that extra 10% of infiltration worthy of the cost associated with the extra media? Well, that's a site-based situation, but you at least can see that it can matter, all right? Now, another benefit of having deeper media with respect to certain pollutants is like temperature. Again, only a few of you, well, a few of you, still maybe like 20, right? We're interested in thermal pollution, but you can see here that 120 centimeters or 4 feet deep media, you have cooler temperatures and more stable temperatures, certainly than you do at 1 foot or 2 foot deep of media. So certainly, if you're worried about thermal pollution, deeper media certainly does seem to have a legitimate benefit. Nitrate, this is one of those slides from Dr. Davis. You see a turtle in the upper right-hand corner. And after about 3 foot of media, you start seeing some actually reduction in nitrate, whereas with less than 3 foot of media, the nitrate removal was not reliable. All right, so again, this is a case where a pollutant that more media seems to matter. We studied a bioretention cell in Wilmington, which is one of our coastal cities where we have pathogen TMDLs and pathogen concerns. We monitored this one for a little over a year, and it only had 20 inches of media, so it was a very shallow media depth system. And you can see how well it worked. And the answer is it worked awesomely, right? We took out 93% of the E. coli that came in, and the effluent concentration of E. coli was really, really low. So in this case, minor media depth, still great performance. So really what it comes down to is like, what pollutants are you worried about? And let's say you're worried about sediment. Well, guess where sediment's captured? The surface, right? Sediment gets strained at the surface. So you don't need to have 4 feet of media to trap sediment. A little bit over half of the phosphorus that's out there hitchhikes with sediment or particulate matter. And so if you're straining sediment, you're also straining about half of phosphorus. Now, the other half of phosphorus, or third to half of phosphorus, is a little more complicated. It's in the dissolved state, and that will tend to get removed in the upper layers of media. So those pollutants tend to get removed at the top or towards the top of the media column. Now, temperature, as I mentioned before, the deeper it is, the better, all right? Nitrogen, you know, deeper systems certainly are better as well. So you'd certainly require more media for trying to remove temperature and nitrogen. But if you get back to pathogens, they get removed at the surface. Metals get removed towards the top of the media, and oils and greases tend to get trapped at the surface and then get broken down. So I guess my take-home point is, I think, pretty clear. If you need to remove pollutants or specific pollutants you're trying to remove, that can really dictate how deep your media needs to be. Now, I know this paper is getting close to a decade old. I still love it. I honestly, I don't think it's dated. I mean, just a smidge, but I mean, for the most part, it's still it's some work I did with Doctors Davis at Maryland and Traver at Villanova. And we suggest how deep your media depths need to be for certain pollutants removal. Okay, and so the take-home point for all of this is media depth can absolutely be targeted based upon the type of pollutant you're trying to remove. So sediment, pathogens, shallow systems are going to work fine. If you're trying to get rid of nitrogen or temperature, deeper media depths are going to be needed. So there's an answer to the first question, which brings us to the second question. I got this bioretention cell. I've had it for a while. I've been maintaining it okay. Is it still working? All right. And a lot of people have been asked this because, frankly, I mean, bioretention cells have been used in Maryland, but for over 25 years. So these practices are getting a little bit longer in the tooth. I'm going to demonstrate, I'm going to answer this question with a couple of studies that we did. We did a project in Charlotte, which is North Carolina's largest city, about 15 years ago. And we looked at how well a bioretention cell worked then, all right? And then 11 years after that study was done, we got a call from my buddies in Charlotte and said, hey, we are interested in, but not interested, this bioretention cell is going to get taken away because they're building a light rail station. Would you be interested in doing some destructive testing, basically digging holes and mimicking up the surface of the bioretention cell? So what do you think my answer was? It wasn't just yes, it was yes, of course, I'd love to do that. And so this is what the bioretention cell looked like per one map, North Carolina. So water came in from the parking lot, entered a 4-bay, spread out across the footprint of the of the bioretention cell, and if the water level got sufficiently deep, it overflowed. And you can see the student going down there, collecting the samples, digging holes, all right, sending these things off to the NCDA lab and the like. And basically, he took samples from everywhere you see the bullseye, and basically from the forebay, which is just getting covered up now, and from the balance of that bioretention cell. And from that information, we were able to create a heat map. And a heat map shows you where you have high concentrations versus not having high concentrations of pollutants. And you'll see we looked at zinc and copper and phosphorus and humic matter. And anywhere that's green, well, that means you've got plenty of capacity to capture that copper or that zinc or that phosphorus. Anywhere that's red means you're getting close to the edge of capacity. And then yellow is obviously somewhere in between. Well, if I go ahead and place that forebay on here, boop, there it is, you can see that the forebay makes a huge difference in terms of the heat map. Like, that's where the pollutants are being trapped, all right? So if you have a forebay in there and the pollutants are being trapped there, and you are doing an occasional maintenance to suck out the accumulated sediment, that means you're prolonging the life of the rest of the media, which at this point in time is green. And in fact, we did a calculation based upon the pollutant loadings that we had looked at from 11 years prior. And you can see that these systems are going to last a long time. You see 300. We actually had to recalculate it, and the numbers are not quite right. What you see here, I need to update that, but it's still like 500 years, 100 to 500 years. In other words, we're all going to be gone. It's not going to be, the zinc and the copper are not going to fill this media up while we are up vertical on this earth, all right? So long story short, the inclusion of a forebay means that a bioretention cell can work a pretty darn long time at removing things like metals, which I think about 8% of you were concerned about. So we have excess capacity, particularly for metals. But what does it mean from a nitrogen and phosphorus standpoint? Does a bioretention cell work long-term for nitrogen and phosphorus? And so another chance to go back and take a look at an old project. This was my PhD research 20 years ago. That's crazy. It's 20 years ago. It looked like that. That's before I had 5 kids. I'm aged a little, and that's okay. I'm not complaining, but I'm glad I'm still here. All right, so that's what. And then 16 years later, we had an opportunity to go back, and I sent a new PhD student, not mine, or my PhD student, but not my research, to decide again to study it to see did it work. In fact, if you take a look, the housing, the equipment housing, you might see it, is the same. The trees have changed. The vegetation has changed. All right. So I'm going to explain to you now. I'm going to go through both the nitrogen and the phosphorus data that we see here, and I'm going to sink my teeth a little bit into this data, into these data. Take a look at those red boxes. That's the range of concentrations associated with the initial monitoring period that occurred in 2001, 2002. The blue boxes are the range of concentrations that occurred in 2017 and 2018. Okay, might have been 2016 and 2017. Anyway, you get the idea. 15, 16 years later. And so then you see in and out. So the in is how much came into the bioretention cell. The red in is in 2001, 2002. And the out is what left the bioretention cell in 2001, 2002. We'll just take a look. In general, the blue boxes show decreases and the red boxes do not. It shows up again with phosphorus. Look at the box to the right. That's the total phosphorus. You see the red, the concentration of phosphorus actually goes up in 2001, 2002. Without anything other than maintenance being done, the concentrations go down in 2016, 2017. All right. Long story short, this bioretention cell works better with time. So why is that happening? Well, number one thing that we attribute it to is the maturation of vegetation. Vegetation is our long-term friend, and vegetation is proving to be perhaps the single most important factor to long-term resiliency of not just bioretention cells, but other stormwater control measures in general. If you want a resilient stormwater control measure, you'd like to see some vegetation in it. All right, certainly for a surface stormwater control measure like bioretention. Now, what does this mean in the end? Well, it means that when we start setting standards for how well a bioretention cell will work in a certain jurisdiction, it's often based on research that's been done in that jurisdiction. And that research tends to be done on newly installed practices for various reasons, all right? But what we have gotten a glimpse of is that perhaps these initial assessments are actually undervaluing how well bioretention works over the course of the long term, that we may be getting even more for our money than we've credited ourselves for. It's good to know, good to know. Now, we also took a look at bioretention cell media as it aged, meaning as it went from, we looked at 28 sites, we looked at them from 1-year-old cells to 18-year-old bioretention cells to get some sense of how, what the content of the media and answer some questions from a design perspective. And so, for example, one of the things you might see here, and this is actually a bit of a negative, that the carbon-nitrogen ratio with time tends to be going down, all right? You want your carbon-nitrogen ratio to actually be above that green line because that enables more active biological transformation of nitrogen. So you'd like to, but this other thing we looked at is like embedded phosphorus. Like as the bioretention cell is in the ground and phosphorus keeps coming in, do you start seeing spikes in phosphorus concentrations? And yes, there is a trend towards higher phosphorus concentrations with time, but even then, only one of the 28 sites that we studied was in the red zone, which means anything in the green zone or even in the lower part of the yellow zone has capacity to remove phosphorus. And we're seeing that bioretention media does appear to have, an opportunity to sequester more phosphorus even as they age. Okay. Now, the other thing we're able to do is take with those data, which, by the way, in the end suggests that they're able to work for a longer period of time. You can then take that data and then you can run a random forest. It's like a decision tree, but fancy computer stuff. And you can take a look at the most important factors associated with higher carbon and nitrogen ratios or higher or lower levels of embedded phosphorus in the media. And you can see things like a forebay stands out as something that if you have a forebay, that means the balance of your bioretention cell likely has a more favorable carbon to nitrogen ratio for nitrogen removal. And if you have, this shouldn't come as a shock, as you have deeper media depth, you're likely to have lower phosphorus saturation across the broad spectrum of your media. But one thing that stands out for both of these is actually the presence of a forebay. That if you have a forebay in a bioretention cell, you tend to have lower fractions of phosphorus in the balance of the cell's media, and you tend to have higher carbon to nitrogen ratios in the balance of the cell's media. So a forebay certainly does appear. If you're trying to get a bioretention cell to work for a longer period of time, the presence of a forebay or the inclusions of a forebay seems to matter. Which then gets us, we're going to come back to that a little bit, what gets us to a discussion on retrofits. And what are some things you can do to take a practice that, I'm just going to be honest, works well to begin with. Bioretention, part of the reason that bioretention came to be and it's stuck around so long is it works well. And that's the reason why things like Filterra work so well. Is it's modeled, it's a rapid flow bioretention system. And so we know that these systems, bioretention or a version of it like Filterra, they're going to work for the long period. They work well. They work well. The question is can you make some of these systems work better? All right. And I'm going to talk about 4 different retrofits to look at. The first and foremost is the one I think is the cheapest, the easiest, and something called internal water storage. You're like, okay, Bill Hunt, what is internal water storage? We're going to start off by describing what it is a change from, and it's a change from normal under drainage. Here, take a quick look at that. I got to wet those vocal cords. So you can see the under drainage ties into the drop inlet. You put your gravel on it, right? I mean, this is the standard under drainage that we've got. It looks like this. This is what most jurisdictions have had in their design 20 years ago, 15 years ago. But we are seeing some jurisdictions, for example, in North Carolina, that requires a change. And the change is simple. That under drain, instead of tying directly in at that same elevation into the drop structure, you want to actually elevate that under drain before as it ties into the storm drain network. All right. And the idea behind it is you basically create a zone internal to the cell that stores water. This practice goes by another name called saturated zone in some parts of the world. I do not call it saturated because you'll see that sometimes when we do it, the media just does not stay saturated. It just doesn't say, you don't have prolonged saturated conditions. You'll hear some people call it a saturated zone. That might be all right, but I personally like internal water storage because it doesn't assume saturation. So what does it look like? When you look at it as it being constructed, here's an example. You see these under drains. You can see the upturned elbow essentially in it. This will get buried with media. This is not the type of design that we recommend now. This is an earlier version. It's a little harder to work on if you have to dig to get to it. An easier version is when you tie in a T or an elbow in your outlet structure and basically force the elevation to occur from your outlet structure. And you can see that occurring with the T right here, a little bit of a standpipe, and that the elevation that the water is spilling out, you can take that elevation and just go right onto the cell and understand that you have gravel saturated and some fraction of your media is saturated at that elevation. It's really that easy, okay? It is an option that you can employ during construction. In North Carolina, it is a requirement. So it's not a retrofit in our state anymore. I mean, it can be, but new systems have to have it. But as a retrofit, it's a very easy retrofit. You can actually see the elbows constructed before they're appended onto or placed onto the existing drainage, under drainage as it came into the outlet structure there. So it's a very simple retrofit. So again, why are we a big fan of it? Well, you can imagine if you put internal water storage in, all of a sudden you are capturing a fair amount of water and temporarily storing it in a gravel storage zone in the bottom layers of your media. And that water has a great opportunity to exfiltrate into the underlying soil. And so in the end, including internal water storage has proven in North Carolina to be a great infiltration or exfiltration enhancer. All right, let me demonstrate that for you. We looked at a pair of bioretention cells in a place in Eastern North Carolina, and I want to draw your attention to the sandy clay loam part of this graph. All right, that if you're familiar with soil types, sandy clay loam is a hydrologic soil group C, as in Charlie soil, which means it's tight. It's considered a generally tighter soil, and within internal water storage zone, depending upon its depth, the thickness of the internal water storage zone, we're able to put between roughly 70 and 80% of the water into the ground. That's pretty amazing. Now we've also modeled it, and this is a water fate for a 3-foot media hydrologic soil group C soil with conventional drainage, no internal water storage. All right. And if you add your purple line to your black line, you have nominally 15% of the water is either going into the ground or evapotranspiring. Okay. Now I'm going to take that exact same site, and all I'm going to do is put an internal water storage zone. That's all I'm going to do. Put an elbow on there, create internal water storage, and instead of reducing about 10% of the volume, we're reducing between 35 and 40% of the volume. All right, that's a big difference. All right, let's say a 3.5 time multiplier by making a very low investment. We'll talk about how inexpensive we think it is in a little bit. All right. Exfiltration is not the only benefit, I might add. There's been some work done at Villanova University with a closed system or a line system, where they had massive amounts of evapotranspiration because you're keeping more water present in the root zones. Now that number is probably, I'd bet most of the money on my wallet, higher than what you get in a normal field site, but still the benefit is there, increased evapotranspiration. Another benefit you get is that when you keep water ponded internal in a cell for a while, you actually get to reduce nitrogen. And we did a meta-analysis where we took a look at all the bioretention studies in and around North Carolina that had conventional drainage, and you can see the nitrogen removal, versus the nitrogen reduction of nitrogen concentration in internal water storage zone bioretention cells, and you can see it's like an improvement of a factor of 5. All right, bioretention with internal water storage knocks down nitrogen concentrations at a very high clip. So when you take in the benefits associated with 1, reducing your volume, so you have less volume leaving your bioretention cell. 2, knocking down the concentration, you multiply the volume and the concentration, the lower, you get massive load improvements. And then in places where there's nitrogen and phosphorus markets, you can sell this stuff, right? So there is a real financial motivation here. Now, how much does it cost to put PVC pipes on the end of your under drain? Not a whole lot. And I honestly think $200 is being cautious. I think it's less. I really do. In fact, if I had a grad student do it, it would cost me about $18.47. But it's here. Now, North Carolina, there's actually mechanisms to help encourage these retrofits to occur. I won't get into that unless we have some Q&A addressing it later. But the point is that there are some jurisdictions now, statewide jurisdictions, where this type of retrofit really can get some steam. Okay. A second option for retrofitting a bioretention cell is to add a media. And most of this research has actually been done by colleagues either at the University of Maryland or at the University of Minnesota, both great schools, great stormwater researchers there. I'm going to just briefly touch on the water treatment residual. It is an aluminum-based product from water treatment plants, not wastewater, but water, all right? And what this graph shows, and it's a busy graph that Dr. Davis, I borrowed from Dr. Davis, but I want you to look at the yellow line and the green line. That is what happened after Dr. Davis took a standard bioretention cell, amended it, and tilled water treatment residuals down for about 15 inches. The concentrations of phosphorus here went from the yellow line down to the green line. If you take a look, that's over a 50% reduction, a major improvement once he added. And if you compared that to the earlier data collected, there was no improvement. So clearly the addition of a water treatment residual that can help capture dissolved phosphorus is a worthwhile retrofit in certain, especially phosphorus sensitive watershed bioretention cells. You might be asking, dude, how expensive is it? Well, the answer is free. It is a waste product. Now, to be fair, you do have to get it from the water treatment plant to your cell, but this is a waste product and they're just happy to get rid of it, all right? The biggest issue with it right now is it's hard to spec it. You know, different water treatment processes will produce different types of water treatment residuals, but they almost all are going to be based in aluminum, and therefore, on the surface at least, makes sense for as an addition or as an addendum to a bioretention cell. Now, a third option is to put mushrooms. Now, some people, mushrooms have gained interest for all sorts of reasons. My specific mushroom interest is the stormwater, all right? And the idea is if you put mycelium or mycelia in a bioretention cell, can you improve certain removal efficiencies of pollutants for certain pollutants? And there's different ones to select. We particularly went with the tiger sawgill mushroom, Letinus tigrinus. Sounds pretty fancy. And the way it was done is they took the spawn, they mixed it with sawdust, and then after they got that well mixed, they put it into a hardwood chip and inoculated hardwood chips with it. And then they took that mix and put it into a jute mat and rolled it up to create these wattles. They cared for the wattles, they watered them, and then after 2 months, we brought it down to the research site in Wilmington, and you can see what it looked like. No, it is not the most attractive retrofit, I will grant you that, but it was a grass cell with these wattles, and you can see what it looked like after as we were monitoring it. So just keep in mind that we monitored the site for a year, a little bit over a year actually, all right, and then put these retrofits in, give retrofits a little bit of time to get acclimated, and then we monitored it again to take a look to see how much additional improvement we got for removing pathogens, and the answer is none. Now, it didn't make it worse, but we sort of were bitten by the fact that the bioretention cell worked great before we did any retrofits, and to be fair, it's hard to make great be better, and we didn't. We did not improve great, okay? So the jury is still out on this. We're actually looking at the same type of study at a pair of cells in Raleigh, and we're looking at nitrogen and phosphorus, particularly in that cell. We'll have those data at the end of the summer. The last option for retrofitting is something I teased earlier, 4-bays. 4-bays are not required, but they're recommended. We think if there is a single input to a bioretention cell, that it really probably should be a requirement. 4-bays, you know, have a wide variety of appearance, some of them more attractive than others, all right? They can become wetlands, for example. We won't get into the trials and tribulations of 4-bays, but including them does make a difference. As we talked about, you include a 4-bay, you preserve the life of the media for other pollutants, which makes a lot of sense. If you include a 4-bay, you remove phosphorus, you'll have more capacity for phosphorus removal, and it appears you also have better conditions for nitrogen removal. So 4-bays seem to be a potential retrofit. So if I'm going to summarize those retrofit options, I spent a lot of time in internal water storage. There is a reason, because it's cheap, it's easy, and it works, all right? Media amendments, particularly if you're worried about getting rid of phosphorus, using a water treatment residual is a pretty inexpensive and relatively easy way of making your bioretention cell do a better job of removing phosphorus. and 4 bays a more expensive option, but it is a retrofit option where it presents itself. So in summary, you've made it, folks. In summary, the deep intermediate depths are not always necessary. They may be for temperature. You want to provide more contact time. Vaco, Alan may talk about an option that I know Contact offers that you guys could consider. But shallow intermediate depths can work for certain pollutants. All right, bioretention cells like a fine wine. It improves with age. All right, particularly if it's appropriately maintained. Internal water storage is a great retrofit opportunity. Water treatment residuals are quite good. 4 bays where it's appropriate, and we don't know enough yet on mushrooms, frankly, because the study was inconclusive. But that is an area of future research. So with that, I want to thank everyone's attention. It means a lot to me that you decided to spend an hour of your time today, and I'm going to turn this back over now to my good friends at Contact.
Well, before you go away, Bill, I'm going to ask you one question that's been coming in from the audience.
You bet.
The first one is, aren't TSS and NNP loads very closely related?
Okay, great question. TSS loads and phosphorus loads are particularly well related because roughly 55–60% of phosphorus hitchhikes on particulates. The nitrogen load is somewhat more independent of TSS loads. But I will say this, I don't hit this hard in my presentation. In fact, you have to really listen. Maybe I didn't even do it. That bioretention, no matter what, removes sediment. It just does a great job. The biggest issue is having too much sediment so that bioretention cells get blinded. But as long as you're not exposing your bioretention cell to a lot of sediment, bioretention will remove 80, 90, 95% of the sediment that comes in. Great question. Thanks for asking. And I'll see you all
Thank you,
later.
Dr. Hunt. And now I'll turn it over to Vaco to continue.
All right, away we go. I'm going to move through this fairly quickly so that we have time for good questions, because I love to hear what you have to say, not just be up here talking myself. So thought I'd zoom out here at the beginning and just take a look at where we are as we approach 50 years since the Clean Water Act, and about 35 years since we've been doing NPDES stormwater management. There is a lot of work left to do. You can see the different waters assessed here. I'm just going to move my window screens around a little bit. Yeah, so different types of water bodies have been assessed at different proportions. Wetlands around 1.2, all the way up to bays and estuaries at 63%. Bottom line is we have about 74,000 TMDLs across the country affecting water bodies. And we're making some progress, but it remains that a lot of the pollutant sources that were causing the biggest issues back in the 50s, 60s, 70s that led to the Clean Water Act are relatively improving. Things like agriculture, industrial stormwater discharges, wastewater treatment plants. However, stormwater as a source is kind of remaining steady, or actually even increasing a little bit as our urban area increases. So we have a lot of work to do. That's the bottom line there. So when I look at the BMPs that we have to do this work, we're going to look specifically at bioretention here. But I group them into two categories, one being conventional systems or non-proprietary systems, the other being manufactured treatment devices. So the difference is kind of how they're treated in permits, at least as I see it. So typically every permit is going to have your standard suite of conventional systems, be it ponds, bioretention, swales, sand filters, those sorts of things. And typically those BMPs are literally the definition of compliance, where if you are working on a land development project and you put in a bioretention cell of thus and such size and infiltration rate and all that, you are deemed to be in compliance with the water quality standards of that permit. That kind of approach leaves not a tremendous amount of incentive to do additional research. And thankfully we have people like Dr. Hunt and others that are doing groundbreaking research on bioretention and advancing the state of the art anyway. But a lot of permittees are just not motivated to conduct that research, in that it, excuse me, at best can really just confirm what you've been assuming anyway, and at worst can contradict the assumptions that you've been making about performance. Manufactured treatment devices, though, receive a little bit more scrutiny, and rightfully so, because typically we are kind of pushing the envelope a little bit in terms of hydraulic loading rate or system size, reducing system size. So we're typically trying to show performance relative to one of two standards that are shown here in the slide. One is, are we at least as effective as conventional systems, or we may be asked to show specific effluent water quality standards or removal efficiencies that line up with a particular vulnerability of a receiving water. And there is a robust community of researchers working on these questions and optimizing and developing new treatment systems. And if you look across the industry, it's a pretty puzzling picture sometimes to try to wade through all the different bits of research and try to compare one to another. There are over 50 manufactured treatment devices out there that are currently marketed, and that's before you start counting all the catch basin inserts and inlet excluders and other types of systems. And these systems are constantly evolving, so it can be a challenge to keep up with the research. Thankfully, there are verification and certification programs out there that we can borrow information from that are doing kind of the deep dive into the data to make sure that whatever performance claims are made are actually met, at least in the water quality testing that is done to get these certifications. So in the previous webinar, we talked a little bit about the Washington Take program and a little bit about the New Jersey program. So I'm not going to go into those specific programs much, except to just note that there are verification and certification steps for each of those programs, and those steps are different. So verification really is concerned with answering the basic question of, was a treatment system tested following a specific protocol, or the Quality Assurance Project Plan, or QAP as we like to call them? And if so, was the performance claim that was made met? And that performance claim can really be water quality, hydraulics, like did you reduce peak flows or infiltrate a certain amount of water as expected? Or how was the longevity? Did you make your minimum maintenance interval or achieve the load capacity, of sediment, for example, on the surface of a bioretention cell? And typically these verification processes have a peer review process where you may actually, or you should have an independent body verifying the data. So reviewing the protocol, the test results, and essentially verifying that those results are accurate. Now, once that verification step is complete, then you get to the certification step. And the certification step is really a regulatory process. It's basically asking the question, does the level of performance that is verified here meet my regulatory requirement? And if it does, then a certification would be granted. And you can see here that both the New Jersey and Washington Take program do issue certifications at the completion of successful testing. And there are many other agencies throughout the US that also use the results either of the verification or certifications that are issued by these programs or by other programs to issue their own certifications. So the point of all this is really just to say that you don't have to necessarily dig into all the data, which can be very hard to compare one to another, especially if it's conducted or collected following different protocols. You can go to those verification and certification resources, especially the ones listed here, and make a lot less work for yourself. So in my last slide here, I'm just going to look toward the future, peer into the tea leaves, or the ferns here in this case, and point out a few trends that I think are important here for the stormwater industry, especially as it relates to bioretention. So the first is the increased reliance on standardized protocols and verification processes. Now, as I look at stormwater, especially as compared to wastewater and drinking water, kind of our sister agencies here, stormwater really just feels like a fledgling industry, kind of in its infancy almost, where we're just now getting to the point where we have standardized testing requirements and protocols, and even just it's been this past year that ASTM has formed a stormwater control measures committee to deal specifically with stormwater control measures. So that to me is a great step forward that I think means that we are moving toward more standardized research and results, which I think is helpful for everybody. Now we all work on these systems, designing them, installing them. Hopefully we're also working on maintaining them at the same time, but this tends to be the most kind of overlooked or neglected part of the process. To me, it's just kind of amazing that that is true, because so much of the work in terms of the cost and complication of stormwater control measures is in the design and the implementation. So maintenance is kind of the low-hanging fruit. There are definitely some innovations here and some research that's ongoing that we're doing at Contech and in other places to look at ways to indicate maintenance is needed easier. For example, maybe automated or sensors, things to put into stormwater treatment systems that will notify you when maintenance is required, and also trying to close the loop at the municipal level to make sure that as we're tracking systems, which is required in virtually every stormwater permit, that we're also tracking maintenance condition and the jurisdictions are enforcing the maintenance requirements that are set at the project approval point. And as we are maintaining these systems, we're removing tremendous amounts of materials from them. It'd be great to be able to quantify those materials and to take credit for the water quality benefits that we're providing, or similarly, the water quantity benefits that we're providing. So this could look like physically measuring the amount of materials that you're taking out of these systems, doing concentration tests, for example, for phosphorus or nitrogen, or instrumenting these systems to keep track of water volumes in and out and water volumes lost to evapotranspiration or infiltration, for example. Another area that I think is ripe and emerging is conformance assessment requirements. So what we're really interested in here is making sure that whatever is delivered to a site and installed actually meets the specifications for it. So it's very easy to have a specific detailed bioretention soil media specification, but feedstocks are different for compost, for topsoil, for some of the other components, and you don't necessarily know if you're getting the right organic content, the right nitrogen and phosphorus ratio, or some of the other characteristics, especially grain size. So having that kind of chain of custody, look backwards to see where your materials are coming from, and then testing of installed systems to make sure that they're actually meeting both the physical and the performance specifications that are set for them is really important. And we're seeing that loop be closed more and more commonly, so that engineers, as they put these systems in, are having to go back and certify to the regulatory agency that they've actually installed something that meets the specs. And the last one here really is kind of a bridge to Tamara's part of the presentation. WEF recently, Water Environment Federation, recently conducted a survey to find the stormwater funding needs of MS4s across the country. And they found that we have a gap of about $8.5 billion annually between what we have to spend on stormwater infrastructure and what is actually needed to meet our water quality goals. So when you think about that gap, that's just a huge number, and it really becomes even more critical to be spending any dollar that we spend on stormwater management on solutions that give us the best and highest solution in terms of water quality and quantity goals. So as we start to manage stormwater at the watershed level, a lot of interesting things emerge from that. We can talk about credit trading and other things at another time, but one of the things that is pretty consistently coming out is that while you can put in bioretention cells and systems on a site-by-site basis or a block-by-block basis in a retrofit situation, it typically is much more cost-effective to be installing these systems at a larger scale. There are just economies of scale that are very important and useful here to consider. So whether that's a regional retrofit type system where you use one system instead of many, or whether you're aggregating new development sites into a more centralized location, that tends to be the best bang for the buck, even if it doesn't perfectly fit within the distributed small scale low impact development kind of definitions that we're all used to. So with that, I'm going to turn it over to Tamara and look forward to questions at the end.
All right, hi everybody. Thank you so much, Faco. I'm Tamara Mammon, and I will be going over just a few case studies that showcase how Contech can help on these large regional scale projects using our Filtera biofilter. So using tested, verified biofilters on regional projects helps to minimize the risk on the treatment, installation, and maintenance issues. The city of Redmond, Washington lists 6 key benefits to using a regional scale approach of design. The first one is that it maximizes utilization of the usable land. It also reduces total capital costs and reduced operation and maintenance costs. There is a higher assurance of the maintenance of the systems with them being centralized. And there's a retrofit potential for existing areas that can also offer aesthetic, communal, and other benefits. The first case study we'll talk about is at University of Washington along the Tacoma Prairie Line Trail. This was installed in summer of 2014 and was the first regional stormwater facility to be installed using high-flow biofiltration. The system manages the flow from approximately 42 acres, sized at 85% imperviousness, and has a total system footprint of 3,300 square feet, which is divided into 6 cells. There was a pretreatment unit used prior to the biofilter to remove trash and larger particles. 3 alternatives were explored for this project: underground detention storage and manufactured filters, traditional rain gardens, and Filterra. Traditional rain gardens could not be used since there was not enough space at grade to fit the system. Only 78% of the annual runoff volume could be treated in the available area when 91% was required. High rate biofiltration could treat the 91% annual runoff volume, and it would only have a footprint of the 3,300 square feet. So using the smaller footprint also led to drastic maintenance savings, which is ultimately the reason why Filterra was pursued for this project. The second project we'll discuss also is installed in Tacoma, Washington. It is called Point Defiance Park. Now, this project treats 754 acres of mixed use and residential area, so a much larger scale than the previous one we discussed. There are 9 cast-in-place units that are tiered into the hillside. These units use cascading inlet bays to collect and divert the flows to each individual cell, as you will call them. Point Defiance Park was installed in fall of 2015, and it uses the steep topography of the site to assist in the flow distribution, as well as having specially designed flow controls to allow for exact calibration, which you can see in the picture below. In order to manage the 754 acres, designed at 50% imperviousness, the total system footprint needed to be 5,500 feet squared, and these were divided into 9 cells. A CDS unit was used for pretreatment prior to the biofilter on this project, similar to the last one, and similar to the last one was also selected for its maintenance benefits. So alternative considerations on this project were traditional improvements like a pond, rain gardens, and Filterra. Again, due to the sheer size needed to treat the 754 acres, the pond and traditional rain garden options were not feasible, with both footprints much too large to fit in the space available. A decentralized approach was looked at for the rain gardens, and it would encompass 300 units spread across the entire basin. So while the 91% annual runoff volume could be treated using the 300 decentralized units, the maintenance costs were exorbitant and made the $85 million 20-year life cycle cost infeasible. Filterra was the clear choice on this award-winning project because it could meet the annual runoff volume treatment requirement of 91% with an installed cost of $1.5 million and a 20-year life cycle cost of $2.2 million. Some feedback we got from the City of Tacoma maintenance crew is that they love maintaining the one centralized unit, and it typically takes them 1 to 2 days versus having multiple units scattered throughout the city. The final case study we'll touch on is Avion Burbank. So instead of pursuing one large biofiltration facility, kind of like the last 2 we discussed, this one uses multiple standard vaults. Avion Burbank is a 60-acre mixed-use development that installed clusters of offline Filterras in parallel, and was sticking close to the standard designs. This helped meet the tight timeline on this large commercial warehouse project. We're starting to see more and more of these projects with tight timelines as e-commerce continues to rapidly grow. Avion was installed last summer and has 42 offline Filterras and 2 Filterra internal bypass curb units. All these Filterras were sized to be alternates to attachment H of the LA County MS4. The 2 large clusters of Filterra are pre-treated by CDS units, and following the CDS units, there is a pump that distributes the flow through the manifold shown on the right so that water will get to each and every unit. This project truly showed Contech's dedication to helping our customers meet their needs. So during the design phase, the stormwater consultant reviewed site plans with the engineer of record and provided product recommendations Simultaneously, the stormwater design engineer was working on the site-specific details. When it came time for construction, the project coordinator managed all the manufacturing and delivery details with the contractor, and we had on-site field consultants to oversee the supervision of installation. You can see this at the picture on the bottom, where a field consultant is overseeing the media install into the large Filterra vault units. This concludes our presentation for the day, and we would like to thank you for tuning in to our second series of the Filterra webinar. At this time, I'm going to hand it over to Joe Black, and we will proceed with some questions. Thank you so much.
Thank you, Tamara. So yeah, just a reminder, if you have a question, type it in the box and I will ask it at this time. Looks like most of these are for you, Dr. Hunt, so I hope you're ready. Are these results affected by seasonal variations? If the retention cell results are vegetation dependent, what happens when the vegetation goes dormant?
Yeah, that's a great question. It depends on the pollutant, but the answer is yes. We have seen the systems do not work as well in the winter as they do in the summer, spring, and fall. Fortunately, we do look at annual load reduction as our metric. And so the good performance of the summer does outweigh the poorer, balance out, even more than just balance out the poorer performance during the winter. But that's for nitrogen. And for other pollutants like sediment, it's going to work pretty much the same way all year long. So it's really only for biological processes that the winter does make a difference. Nitrogen being first and foremost. To a lesser extent, pathogens. Pathogen removal is not as good in the winter, but on the flip side, pathogens tend not to be as much of a concern in the winter either because people aren't in the water and being exposed to them. Good question.
Thank you. Our next one is, how do you design or size 4 bays for bioretention cells?
That's a great question. I wouldn't tell you the easiest way to do it, though. I would always encourage you guys to go to your sediment and erosion control manual that's used in your jurisdiction and look how they say you should size it. All right, but dedicate 10% of your surface area, of your bioretention surface area, to your 4-bay. If you do that, it's an easy rule of thumb, but that rule of thumb has proven to be a pretty reliable one too.
Next question, does the saturated area work in areas with really low infiltration rates like type D soils, or would they not be recommended?
Yeah, they do work, but they work differently. Bioretention cells with type D soils are in use internal water storage are very good at removing nitrogen. Those are like the best nitrogen concentration reducers we've got. They're also better for temperature. They're better at temperature mitigation, particularly if the media is sufficiently deep. You don't get the hydrologic benefit though in type D soils. And so if you are in a place where you don't care at all about nitrogen, don't care about temperature, then, and you have a type D soil, then it probably doesn't matter. But usually people at least care somewhat about the other two, that if you're gonna do it, just go ahead and put the under drain in there with the upturn elbow.
Next question is, what's a range for how much longer the water is stored in IWS?
Yeah, it is a shocking range. It can be, we've done one where it was like 3 hours. Like it was just sandy. It depends upon your underlying soil. And we've also had one where the water, if it didn't rain, you'd have some remnant water for over 2 weeks. So it does range depending on a number of factors, but the principal among them is what are your underlying soil type. Good question.
Thank you. And our last question for today is there issues with the root invasion of the underdrain portion in the retention area?
Great question. No, that has not been observed. Now, could I say that's an impossible? No, I can see that being a possibility, but we have not observed that. And I think part of it may be that there is ample, basically tree roots go to where, when they can't get enough water, they keep seeking and seeking and seeking. And with the internal water storage zone, you're making more water available to vegetation closer to the surface. So if I had to bet, I would bet that internal water storage bioretention cells actually have less tree root invasion problems than non-IWS underdrained cells. Though that's me using a best professional judgment. I don't know that for a fact.
Well, thank you, Dr. Hunt and Tamara and
Pleasure.
Vaco. And thank you everyone for participating in today's webinar. If your question was not answered, a contact representative will reach out to you with a response. A survey will appear once we conclude the webinar. Please complete the short survey to receive your PDH credit. A follow-up email will be sent before the end of today that will include a link with instructions on how to download your PDH certificate. This concludes today's webinar. Thank you again for joining us and have a great day.
Hey guys,
Thank you.
thanks a lot.
Thank you.
I enjoyed this quite a bit. So